Okay, so last time we ended by bisecting the line segment. So bisecting some given line segment was kind of the last construction that we mentioned. Um, and so the same construction bisecting the line segment yields to, so it looks something like this. So I've given line segment AB. If I fix my compass to have radius AB and draw those two circles. Uh, the points of intersection give me another line that bisects AB necessarily. And the other thing that you can notice here is that it's not a coincidence. So going through compass straight edge constructions, when you look at a geometric diagram, the big questions that you always have to ask are how many of the things look this way because of just the way that I happen to draw, like say my initial line segment or my initial diagram, and how many of the things look this way because they have to look this way, right? That's kind of one of the first struggles. So actually proving something via a diagram like this requires you to be careful with how things are drawn, and maybe kind of the best way of thinking about it is just making sure that any markings you make, that things that have to be congruent are congruent for reasons not just because they look congruent, but because they actually have to be congruent. Okay, so for instance, so A and B, these are both centers of circles having the same radius. This line of intersection, or sorry, this these 2 points of intersection of circles, um, C and D form this line that looks perpendicular and in fact has to be perpendicular as well to AB. So this construction of bisecting line segment also gives us a way of constructing perpendicular lines. So from bisecting the line segment, I also have a way of constructing a perpendicular to a given line segment. Or a given line, right? Um, so I can actually uh, do this for a line. I don't need to refer to the length. Talking about bisecting, of course, I was dealing with a line segment because I needed to be talking about cutting a line segment in half. A line being a thing with infinite length, it doesn't really make that much sense to talk about cutting its length in half. Um, for a line segment, that makes sense. But it turns out that I can actually do this construction. When I'm talking about constructing a perpendicular line, if I don't care anything about the length, I could do this for a line, not just a line segment. So to do this, there's two cases. So to do this, two cases. So one, to construct a perpendicular to a line L at a point E on the line L. What do I do? I first draw a circle of some radius, doesn't matter which, centered at E. This circle is going to intersect that line L. We'll call the intersection points A and B. So cutting L at points A and B. Right. Then this gives us a line segment that is part of that line L. I bisect that line segment, right? And this gives me the perpendicular. Then the line CD, as constructed before, is the perpendicular through E. Okay. So that's the way to do this if you are wanting to construct perpendicular to a line at a point E on the line. What if you want to construct a perpendicular to a line that passes through a point that's not on the line? All right, so to construct a perpendicular to a line L through a point E not on L, I do the same thing, only I make sure that my initial circle is large enough, i.e. has large enough radius, such that it intersects L twice. Okay. So I'm not going to draw pictures of either of these scenarios, but and the reason for that is because I'm going to give it to you as homework. This is going to be part of your homework to do this. So, but you can imagine if you have a line sitting somewhere, right, in the plane, and some point not on the line. Well, that point could be really, really, really far away from the line. And if it was really, really far away from the line, if I just draw, in part one, I was allowed to draw a circle of any radius. But if I tried to do that for the second thing, then that circle that I drew, if the radius wasn't big enough, it wouldn't even intersect the line, so I wouldn't be able to repeat this process that I did in part one. So it's really the same as in step one, but the difference is that I just have to ensure that this circle that I draw first is actually a big enough radius that it cuts L at two distinct points. The other possibility, of course, is that if the radius of my circle is chosen to be the exact distance of that point to my line, then it wouldn't cut it twice. It would be tangent to that line, right? That line would be tangent to the circle. And so I wouldn't get 2 points, and I wouldn't be able to repeat this construction. Okay, so it needs to be big enough that it intersects the line in two distinct points. Okay, so here, we're using the possible configurations of circle and line here, right? So a line cannot intersect a circle. It can intersect the circle at a single point. That's when it's tangent to the circle. And it can intersect the circle in two distinct points. Those are the only three possibilities there, right? Okay. So here's these two things. Constructing perpendicular follows immediately from bisecting line segment. Okay. Now let's bisect an angle. Okay, so let's bisect an angle. So let's say I have some given angle, call it POQ, I think is what the textbook calls it. So here's my angle. So here's P, here's O, and here's Q. Okay. So I want to bisect this angle, right? So what is it I'm even bisecting? Where is the quantity? So the angle in question, of course, I'm not going to break out a protractor and measure this or anything, but the idea is that the angle in question is, of course, this amount, right? So I view this as being some amount from zero, so there's an opening up of the angle going on, and it's that this distance of opening is what's being measured here. This is one way of thinking about it. Okay, so bisecting this angle then is splitting it in a way that it is, into two equal parts here, just like bisecting a line segment. And it turns out that the construction that I use here is essentially the same as bisecting the line segment. So we'll see that here. Okay, so what do I do? So the first thing is I draw a circle that has center O, and it doesn't really matter what the radius is. Okay, doesn't really matter what the radius is. So I first start out drawing a circle centered at O. I've opened my, let me make this a little bit bigger just so it makes the diagram more uh, readable. There. Okay, so this is a circle of some radius centered at O. Okay, so what is important is that these 2 points lie on a circle of the same radius. So I label these 2 points A and B. Now, to see the similarity between this and bisecting a line segment, I could draw the line segment between A and B, right? I could actually draw that in if I wanted to, but I'm not. Okay, so I could draw this in, but I'm not going to do that just because it will make the diagram not as tidy. So rather than do that, what I'm going to do is show you, without drawing in the line segment, what it is I do. So if I were bisecting the line segment between A and B, what would I do? I would set my compass to have exactly that distance recorded in it, the distance between A and B, or the length of that line segment. And then I would draw circle of that radius centered at A and circle of that radius centered at B. Okay, so I can still do that. Let me make sure I've got my, yep, okay, that's good enough. So this circle gets drawn. I don't need to draw the whole thing. I can just draw half of it. And similarly, having to dodge the camera makes this harder. Okay. So these 2 circles intersect at points C and D. This is not going to look totally right because I've squished my compass a little bit. So here's C and here's D. These 2 points generate line segment or line that bisects this angle POQ. Okay. So, as I said, note this is very similar to the construction of the bisection of that line segment AB. Okay. So that might lead you to think that that bisecting line segment and bisecting angle, since they're the same sort of construction, really, right? The only difference here between this and the construction I did before was that in the construction before there was no angle showing up here, but what you were doing functionally was exactly the same. But it might lead you to think that splitting a line into any number of pieces is related to splitting an angle into any number of pieces, but we'll see that's not the case. So while bisecting a line segment and bisecting an angle are similar processes, it turns out that while we can divide a line segment into n equal pieces without much issue, okay, using compass and straight edge. There is no nice way of doing this. For a general angle. Okay. In fact, can I even trisect an angle? Right, generally. The answer to that is no. So using compass and straight edge alone, it is not possible to trisect a general angle. Okay, so you can't even cut it into 3 equal pieces. Okay. All right. So this leads us to say something. So note, I'm asking a lot of these questions in a repeated fashion. So to keep things organized, I'm going to try to save some of these big construction problems for last. So there are 2 big questions that keep coming up. So one, what can I construct? When I say construct, I mean with compass and straight edge. Okay. And 2, what is known to be impossible to construct? Now you might think, or you might not think up question 2 on your own, or you might think of question 2 as being related to this, since if you can 100% answer what can you construct, maybe you consider as part of that answer the questions of what you can't construct, right? Since basically what can I construct, if the answer to that is not everything, then clearly there's some things that you cannot construct that it is impossible to construct with compass and straight edge. So what can we construct? We are going to do this. We're in the process of trying to answer as much of this as possible, right? So we're attempting to answer all of this. Okay. What is impossible to construct? I'll try to organize some of the big things to come later. So we'll organize the answers, the important ones, later. Okay, necessarily, I mean, depending on what you're talking about, there's not strict limits on either of these, right? What can you construct? Well, you can always, any given diagram that has ever been constructed, you could take that diagram and then tack on, an equilateral triangle, right? So we're not talking about a trivial way of doing this. We're trying to get a bunch of different stuff that we're constructing here. What is impossible to construct? These are things like I just mentioned, trisecting an angle generally is actually something that's impossible to do with compass and straight edge alone. Another example would be squaring the circle. Okay, is an example. So we'll talk about why that's not doable. And I mentioned earlier that when it comes to constructing regular n-gons, not all of them are constructible. I will bring up the theorem that shows why or which ones are, where that comes from, just because it's interesting. But as it turns out, these questions of what's impossible to construct, because the tools that were required to answer them didn't come until thousands of years later, the answers to these questions didn't come directly from geometry. They actually came from algebra. Okay, and so it wasn't until some algebra tech was invented that it was actually possible to answer these. And then once you have a proper algebra background, the answer to these questions is actually really easy, or I should say is an easy application of the algebra toolbox. So I can give you guys some reference for that because it's actually pretty interesting. Anyway, but it does fall outside of strictly geometry. Okay, so more construction. So on to continuing to answer question 1 here. Um, so constructing a parallel to a line through a given point. Okay, so I want to construct a parallel through or to a line through a given point. Also, not going to draw a diagram of this because I'm going to have you you all do it as homework. So, given a line L and a point P, not on L, first construct the perpendicular to L through P, then construct the perpendicular to, I didn't name it, so construct the perpendicular to L through P, call this the line M. Okay, so call that line M. Then construct the perpendicular to M through P. And that does it. Okay. So, I have a line, I have a point not on line. I construct, so maybe I'll draw a picture. This doesn't actually show you exactly how to do it, but now you know how to do it. So I have line L, that's barely a line, point P, not on L. So first I construct perpendicular, that's M, and then I construct the perpendicular to M through P. Okay, it's a really crude picture, but that's how it goes. Okay. All right, but of course you can actually construct this perpendicular in the same way, same method that we used before talking about what happened after the bisecting of the line. Okay. All right, so I bring up parallel lines because here's where parallel lines become important, because they are going to allow for the following construction. So I want to divide a line segment into n equal parts. So dividing a line segment into n equal parts. Okay, so how do I go about doing this? Well, let's start with, where did I put my straight edge? Here it is. Okay, so let's start with a nice line segment, AB. So here's A, here's B, here's line segment between them. Okay. All right, what do I do? So I take any other line through A. Well, I need a point to determine that line. Actually, I'm not even going to do that. I'm just gonna pick some line here. Doesn't matter. Here it is. Okay, so here's my line L. Okay, that passes through A. It's a bad L. Okay. So how do I divide a line segment into n equal parts? The idea is I first take compass and I open it to whatever radius I want. Okay, so I open it to some radius. That looks okay. Here, let's make it a little bigger. There we go. Okay. All right, and then centered at A, I mark off points along L. Okay, so here's A sub 1, and keeping my radius the same, I now put my compass at A sub 1 and mark off the next point along L. So here's A sub 2. I continue doing that. And let's do a couple more. Of course, you could say, like, how long do I go? Right, how many do I do this for? Depends on how many equal parts you're going to break this into. So here's A3, A4, and A5. So let's do n equals 5 here. So 5 equal parts. Just because this is the same diagram that's done in the textbook. Okay, now if you wanted to break it up into more parts, you would have continued on here. If you wanted to do this really conveniently, you could have specified this compass length to be, this compass distance to be, smaller. But of course, if you needed more room here, in a sense, you could also extend L. So what do I do here? What do I do next? So the next thing is, when I've decided however many parts I want to split this line segment into, I stop at A sub 5. So since n is equal to 5, I stop at A sub 5. And then I connect, or I draw in the line segment from this last point to B. Okay. And then, so after drawing the line segment A sub n B, I then construct the parallels to A sub n B through the points A sub n minus 1, A sub n minus 2, and so on, right? All the way to A sub 1. All right. I construct those parallels. They intersect AB. How do they do that? So there's some questions here, right? There's some questions we have. So the questions we have, first of all, is I keep saying construct the parallel. What does that mean? One, I'm shorthanding this, right? And for that reason, these are not going to be exactly parallel. If you were doing this the proper way, then what would happen here is you would construct these parallels in the same way that you constructed the parallel before, using this double perpendicular construction. So before, we had just talked about how to construct a parallel through a given point. Okay, like I said, I didn't go through the process because that's going to be your homework. But you would use that process on each of these points. And so if you've done this properly, this should split the line segment AB into 5 equal parts. Now again, I was freehanding, well, I wasn't exactly freehanding, but I wasn't doing the proper construction of these parallel lines, so they're not quite parallel, so these lengths are a little bit off. But this is exactly how it would work. Then these parallels divide AB into n equal parts. So in this case, 5 equal parts. If you want to see the exact picture that looks really nice, here it is. Oh, let me maybe not go. There we go. All right, so that's what it looks like. Okay. Now, quick question. Why does this work? Okay. So there's some questions here, right, that we're not going to completely satisfactorily answer until the next chapter. Okay, so there's a little bit of hand waving at this point. One, when I'm constructing these parallels, I'm assuming that I have one parallel that I can possibly construct, right? There's no second option here. What does that mean? So this is, a key property I've mentioned before that this choice of parallel line in this situation is unique. This is going to be like one of the more important things in the course that we talk about over and over and over again. But for now, you can assume that there's only one way to do this. Okay, and so I don't have to worry about the uniqueness of this construction. This is the only way. But the question is, why does this work anyway? So this is a consequence of the Thales theorem, or theorem of Thales. What does the Thales theorem say? That parallel lines cut any lines they cross in proportional segments. Okay, so parallel lines cut any lines they cross in proportional segments. Okay. Well, what does that mean? So, something like that sounds important enough to have some applications that you've seen before, and in fact, you've definitely seen applications of this before. So, one place where you've seen this specifically is in a triangle. So here's Thales' theorem in a triangle. Okay, so Thales' theorem in a triangle is the following. Here, let's start with here's the base of my triangle. Let's just pick a point. Okay, maybe I drew that a little bit too close to being an isosceles, but not quite. Okay, so here's triangle ABC. Imagine I have a line that is parallel to BC. So there it is. So here's my line L. Okay, this intersects the sides AB and AC at points P and Q. Okay, so L is parallel to BC. Okay. So what does the Thales theorem say? It says that this line that's parallel to BC cuts any lines that it crosses into proportional segments. What does this mean in this context? What it means, so Thales theorem says that the length of AP divided by the length of PB, that is the length of AP divided by the length of PB, is equal to the length of AQ divided by the length of QC. Okay. All right. Now, in this triangle, because these quantities kind of look similar the way that I've drawn it anyway, you might not be that surprised in this picture, but actually this would be true even if the triangle was a lot less nice looking. So here's another example of the Thales theorem working. So now I just need another parallel line here. Right. So there. So here's PQ, and here's ABC. Right. So this Thales theorem is true for both these triangles. Okay, this statement is true. You might look at this and say, wait, I've definitely seen something like this before, right? When I've dealt with similar triangles arising out of diagrams. Okay, you might remember maybe like one of the last times you used this is when you're doing some, some stupid like cross-sectional area computation as part of volumes of solids, right? In like your early Calc 2 stuff. The cross section, sometimes you end up with a thing that looks like this, right? That generates similar triangles. And indeed, when we talk about similar triangles, that this Thales theorem is going to be like the centrally important thing. But it turns out that Thales theorem is going to be actually really important, period, because it's going to be the thing that gets us algebra into geometry, and this is going to have a ton of applications. So there's a lot of stuff that comes out of this. Okay. All right. So just what I said here. This is going to be the thing that allows us. This is going to allow us to multiply and divide lengths of line segments. Okay. Okay. We can already add and subtract, right? So multiplying and divide is the only other basic arithmetic operations we need. All right. So, just what I said, we can already add and subtract. That was the first thing we did. So we can already add and subtract lengths of line segments. Okay. But using Thales theorem, we can construct A over B and AB for line segments A and B. Meaning that we can actually identify the line segments themselves with their lengths here and think about what it means geometrically to talk about the product of two line segments or the quotient of two line segments, okay? Not necessarily just their lengths. Okay. All right. So, first, it is necessary to choose a line segment of unit length. Okay. All right. i.e. of length 1. And what I mean by that when I say length 1 is that the symbol here one means to imply that when I multiply this line segment that has length 1 with line segment A, I get A. Okay, and that's for any length A. Okay. All right. So we'll talk about what this means to specify this length in chapter 2. But we can do this. This is not an issue. Okay, and we'll see why that is. So then to construct the product of two line segments, how do I do this? Well, first I have a triangle constructed that is a triangle, looks like this. I'll call this triangle UOA, U for unit, so O, if you like, you can think of as my origin. Okay, we don't have coordinates yet, of course, but so UOA is the triangle I'm dealing with. The length of the segment OU, or UO, U being unit, this is my length 1 segment that I've specified. Okay, and the length of OA is A. Okay, that's given line segment that I'm interested in multiplying by another given line segment B. Okay, so what is it that I'm actually doing here? So what I'm trying to do is I want to multiply line segment B by line segment A. All right, and so what I do then is I construct off this line segment, I extend the line segment UO, however much I need to extend it, until this segment from U to some B sub 1 is exactly length B. How could I do that? Why is that allowed? Okay, so why is this thing allowed? Why is this construction allowed? The way that I could do this is, since this is unit length 1, okay, for all these arithmetic properties that I want to be true to follow, I could just say, well, I understand automatically, I understand what addition to natural numbers is like. And so the way that I could do this is simply just add 1 to itself. I know geometrically I can construct the addition of two line segments. So I could add 1 to itself until this resulting length is B minus 1 totally, right? So this would be B. B plus 1 totally. So this piece would be B. Okay, so then what do I do? Okay, so then I construct the parallel to the line segment UA. Okay, so I have line segment UA, and you might remember this notation. I want to construct the parallel to that line segment UA, and so let's say that I've done that. Okay, so let's say that I've done that. Here's roughly what it looks like. I don't know if I went far enough. Yeah, I think I did. So I construct the parallel to my line segment UA, and when I do that, that intersects the extension of the line segment OA at some point, okay, which I'm going to call C. The length of this line segment AC is then AB. And so, nice visual way of viewing this is going in this way, I am multiplying by A. So I take line segment B, and to multiply by A, thinking of moving this down almost along this parallel. So I'm not actually moving anything. This is just in the picture. in order to multiply by A, I do this construction in this direction where I construct parallel to UA. This line segment I get from the intersection of that parallel with the extension of OA gives me this product. Okay. Why is this the case? Okay. So you might say, why is this AB? In fact, let's pretend for a second that it's not. So let's say this is X. Okay. What is X? Well, by Thales' theorem, what is true about this picture? So by Thales' theorem, I have to say what? Well, one thing I could say is that B divided by 1 is the same thing as X divided by A. So by Thales' theorem, B divided by 1 is equal to X divided by A. But then, what does this mean? This means that X, multiplying both sides by AB, X is, or sorry, multiplying both sides by A, X is AB. And so it was right to have AB here. Okay. All right. So Thales' theorem is the reason why in this construction this segment ends up being A times B. Okay. And so geometrically, the symbol that I'm using for A times B is this line segment. Okay. I know it seems a little strange because you're like, why do I have to worry about defining A times B? You're not defining the multiplication of numbers A times B. What you're doing is you're taking the symbol that is a product A times B and you're constructing geometrically what that picture is, right? Or rather, you're starting with geometric picture and you are coming up with geometric construction that is tied to that arithmetic operation of just multiplication. So how about a quotient of two line segments? Okay. So then to divide line segment B by line segment A, what do I do? I use that same triangle maybe this one looks a little different. So here's my triangle UOA. Okay, so here's side 1. Here's side A. I extend my side OA until I have extended it to be exactly B units, so we'll call this B sub 2, whatever that is. And now I construct the parallel with the parallel to UA in the same way. This intersects the extension of OU, okay, in some point we'll call D. This segment here has length B over A. Okay. By the Thales theorem in the exact same way. Okay. All right. So I think that's all for today. We will finish chapter 1 entirely next time. And then from there, we'll start with the axiomatic treatment of this stuff in chapter 2. So yeah, so on Friday we'll finish chapter 1 entirely. So anyway, I'll continue posting links to the videos in the announcements, and then I may either make a recurring public stream or you just show up to the channel and it will show up around like 5 minutes before class time. So anyway, that's the deal. So I'll see you all Friday, and I'll post your homework here in like another. I have to teach right now, but I'll post your homework here in like another hour or so. Okay. So it'll be very short. It'll be due Friday. It'll be like 2 questions really. Okay. So really short stuff. So anyway, I will see you all on Friday.